So number 17 is an unusual setup. You can see we got this kind of weird spool, has a mass of 200. They give us a radius of gyration, so we're going to use the mk squared term in order to get at a moment of inertia. The whole thing is attached to the wall. There's a cable AB. Okay, interesting. And then there's a moment of 450 on this thing. Now, you can kind of see in your mind's eye that as this thing starts to turn, what's going to happen is it's going to end up moving toward the wall on the right. So it's kind of like whatever's causing this thing to turn is going to cause the cable AB to actually wind around onto that cable. All right. Now, our job is to determine the acceleration, the transverse acceleration, the translational acceleration, the angular acceleration, and then also the tension in the cable. Okay. So let's write out our forces that we've got. And so we've got some tension here. I'll just call that T. And then we've got our normal force, of course. And we've got our weight, of course, mg. Those are the only vertical forces, so we know that the normal force is mg. And then it's slipping across the bottom, okay? The bottom of that thing wants to slide to the right as it moves. Okay, it's curling under, it's to the right. And so that means that the friction has to be the opposite direction on that thing, which is going to be this way. Okay, now luckily it's kinetic friction, so we can know exactly what that is. All right. Okay, and let's just go ahead and calculate that. Okay, so our friction is mu mg, and the value for mu is 0.2 m. It's 200. Man, it's a big spool. And 9.81. So our friction, when we calculate that thing, is, just a second, is 392.4 newtons. Okay. Now, I would like to go ahead and calculate the moment of inertia, just so we can sort of have that handy, because we're going to need that as well. That means we got to figure out where we're going to rotate this thing. Okay. We know the friction. So I'm just going to think about options here for a second. So what we've done before is we've put our pivot down there because we didn't know the friction, and so that turned out to be very handy. This time we do know the friction, so maybe that's not such a good choice. So let's think about, well, what if we just do it in the center? Well, if we do it in the center, then we get a moment from the tension and we get a moment from the friction both. We know friction, we don't know tension. So maybe that's not so great. Okay, let's put our pivot at A. Then the only unknown force, which is the tension, is done. And the only moment that we have is the applied moment in addition to the friction acting on the thing. Okay, so we need the moment of inertia around around A. So we need I sub A. So we're going to need an offset term using the parallel axis theorem. And then our moment of inertia based on the radius of gyration term, which gives us that. And so that's going to be the mass, which is 200. And we need the distance from the pivot point of rotation A to the center of mass, G, which is 0.4. So we got 0.4 squared plus 200, and that's 0.3 squared for my radius of gyration. And once we work all that out, IA turns out to be 50. Okay, just like that. So let's go ahead and start with our moments and see if we can find alpha out of this thing. So we're going to be pivoting everything around the point A. So I'm going to make sure those all say A on them. And so we've got a 450, some kind of moment actually applied to the axle. And then we've got our friction. And our friction is going to create a negative moment. And it's going to act at a distance. We got to go to the center, which is 0.4 from A, and then from the center all the way to the bottom, which is another 0.6. So that just turns out to be 1. And that's our IA onto our alpha. Okay, so we got 450 minus 392.4 times 1. And that's equal to my IA, which is 50 onto alpha. And so alpha, then when you work all that out, turns out to be 1.152. Okay, so far so good. Okay, well, we still have to get the translational acceleration. So I'm going to move up to my next equation, which is going to be, I'm going to do this one up here next. And if we sum our forces, we've got our tension minus our frictional force, and that's equal to MA. Okay, well, now we got a problem. We don't know A, we don't know the tension. All we know for sure is the friction. So we got to get a handle on what's happening with the acceleration. Let's go back to our drawing here. Okay, now here's a new term. Okay, we haven't used this term yet. This is called instantaneous center. The instantaneous center for a given motion is when you've got a rotation and a translation at the same time, but you can identify a spot that in that one moment, okay, doesn't have any angular, well, it doesn't have any rotation to it. Okay, so it's like the center of rotation for the object. And for our situation, point A is that. So sort of in your mind's eye, I bet you can see that this thing, it's kind of like it wants to rotate around this way. Okay. And if we look at it that way, that becomes our alpha, and that is also positive. And we've called this direction here positive as well, which means my alpha and my A values are aligned. Okay, and so we can actually use, even though this is slipping, because we've got this instantaneous center, we can say that A is plus or minus alpha R for that instantaneous center. And they're aligned, so we choose the plus. So we're going to have plus, and our alpha is 1.152. And that instantaneous center is a distance of 0.4 away. So the acceleration is equal to 0.4608 meters per second squared. Okay, so you might want to pause the video and take a look at that. We're able to use that trick because we were able to identify one point where we could call the instantaneous center. Okay. Now, if you cannot do that, then you are going to be forced to go back and contend with our relative acceleration equation. Okay, which looked something like this. Alpha cross RAB minus omega squared RAB. Okay, and we did a lot of homework problems on those. Okay, so what you have to do then is you're going to have to relate two different points on it somehow. And that may or may not be straightforward. Probably not. Okay. But since we were able to identify a point that we could call the instantaneous center, then we can use the trick that we just did to come up with a value for the acceleration here. Now, since we've got that, we can come back up to this relationship up here, looking at our horizontal forces, and we can write that our tension is equal to MA plus the friction. So that makes sense. The tension is accelerating it, and it's got to compensate for the friction. So all that makes sense. And so I'm going to have here that this is going to be 200 onto my acceleration, 0.4608, plus my friction, which is 392.4. And so my tension then turns out to be 484.56. Okay, so it's not too bad. So, but we did learn about a new thing there called the instantaneous center. We've kind of been using that all along when we've done no slip rotation and that sort of thing. But here in this one, you can see where you can take the same idea and use it in certain cases where you have slippage with your rotation. Okay.